in this session, we will discuss about a synchronization problem solution, that is the semaphores. As we know from the previous discussions, a critical section problem must define a process in a structure. The structure consists of entry section, critical section, exit section, remainder section, and the process is executing continuously in a loop. Okay, so any critical section problem has to satisfy three conditions. One, we call it as mutual exclusion, means at a particular time, only one process is allowed to enter into its critical section. Second one is progress. The processes who are competing for critical section are allowed to enter into the competition. I'm repeating, the processes who are competing for critical section are only allowed to enter into the critical section. Third one, bounded weight. The bounded weight must ensure that there must be a limit on number of times or the amount of time a process is allowed to stay in the critical section. It should not create a starvation to other processes. Means the other processes should not wait for a longer time to enter into their critical section. Okay. So any critical section problem has to satisfy three conditions. One is mutual exclusion, second one progress, third one bounded weight. So the solution for critical section problem is provided by using one is called Peterson solution, second one is called semaphores. So using Peterson solution, okay, it is a software based tool provides synchronization among only two processes. For more than two processes, we need to use the concept of semaphores. So in this video, we are going to cover the concept of semaphores. Simply speaking, first, a semaphore is a variable. A semaphore is a variable. It has some initialization. Along with the initialization, we will perform only two standard atomic operations. Those two operations are wait and signal. Okay, the semaphore is a variable which is having some initial value, and that semaphore variable is manipulated or updated only by using two functions. One is called wait, the other is called signal. The purpose of a wait operation is to test the semaphore variable, and the signal operation is to increment the semaphore variable. Weight is called Proberan and the signal is called Verhoeven. Okay, Verhoeven means to increment. Proberan means to test. This weight and signal is also named as P and V operations. We will call them as what? P and V operations. So how the definition of a weight function? The weight operation on a semaphore is defined like this. Continuously check in a loop for the semaphore variable. If that variable is less than or equal to 0, do nothing. Means no operation is performed. Means so and so process has to wait. Otherwise, just simply decrement the semaphore variable. So wait operation is doing what is that? Continuously check the semaphore variable. If it is less than or equal to 0, no operation is performed. Otherwise, just decrement the semaphore variable. Second operation is signal operation. The signal operation purpose is only to increment the semaphore variable. Okay. So semaphore S is having some initial value, and that semaphore is modified by only two functions, wait and signal. Wait is testing for S and decrements, and signal is just increment the semaphore variable. So how these two operations will work with the semaphores? To understand, we need to have some conditions to use this wait and signal. First point, the semaphore variable must be modified only with the two functions wait and signal. Second point, when wait is executing, we should not allow the signal to come into picture. If signal is executing, we should not allow the wait to execute. Means S variable should not be modified by wait and signal at the same time. Third point, when doing wait operation, checking the condition and the decrement, both should happen in the same context. Means in between, the process should not interrupt to some other process. I'm repeating, the testing of this S and decrement both should happen at a time, that is in the same context. The process should not switch, it should not interrupt for any reason when we are doing what? Wait operation. So what are the three conditions? The S variable, that is semaphore variable, must be modified only with wait and signal operation. Second one, when wait is performed, the testing of S variable and a decrement both should happen in the same context without an interrupt. Third thing, S variable should not be modified by wait and signal at the same time. Means when wait is happening, signal should wait. When signal is happening, wait has to wait. Means these two are atomic operations. Only one operation has to be performed at a time. So, as of now, what we understand, what is semaphore variable and what are the operations performed on that semaphore variable. Wait job is just simply test and decrement. Signal job is only to increment. So, how this semaphore variable used for synchronization problems? For that, we need to go with two types of semaphores. Okay. Generally, semaphores will be categorized into two forms. First one, you call it as a binary semaphore. Okay. A binary semaphore is a variable which is having a value either 0 or 1. Okay. The semaphore variable is initialized to either 0 or 1. Initially, the value of the semaphore variable is set to 1. And the binary semaphores are used for mutual exclusion. Mutual exclusion means what? When several processes computing for critical section, only one is allowed. So for mutual exclusion, binary semaphore is used. Initially, binary semaphore value is set to 1 for mutual exclusion. For mutual exclusion. So how it is achieved, we'll see with one example. But the definition of binary semaphore is what? It has the range of values only two, either 0 or 1. It is particularly used for mutual exclusion and also called it as mutex lock. Initially, for mutual exclusion, semaphore variable is set to 1. Okay. So how this mutual exclusion we will achieve, we'll see with one example. Let us suppose three processes are executing concurrently in the system. P1, P2, and P3. Three processes are executing in the system. As we know, because these are having cooperation, because these are the cooperating processes, so every process will have some critical section. Let us assume P1, P2, P3 are cooperating processes so that they have a common section called critical section. Okay. Now we have to use binary semaphores to provide the solution for critical section. What happens, all the three processes commonly share one semaphore variable. Let us call it as mutex, and it is initially set to 1. For mutual exclusion, mutex is initially set to 1. Next, let us suppose process P1 wants to enter into critical section. Then P1 will execute in the entry section weight of that semaphore variable mutex. When I say weight of mutex, what happens? Weight will check for first thing in a continuous loop, it is checking for s less than or equal to 0. Okay. If s less than or equal to 0, do nothing. Otherwise, you have to decrement the semaphore variable. Okay. This is the operation performed by weight system, weight function. Okay. What this weight operation is doing now? S is not less than or equal to 0. Then what it will do? It will decrement the semaphore variable and so that it will become 0. Now P1 enters into critical section. Okay, P1 enters into critical section. Now, at the same time, let us suppose P2 wants to try to enter into critical section. Then what it will do? It will make a call to weight of mutex. When I say weight of mutex, it will check the condition s less than or equal to 0. Yes, here s is your semaphore variable which is less than or equal to 0. So that what it is doing, it has to wait. So what is happening? The process has to wait. After that, let us suppose P3 also trying to enter into critical section. Then what it will do? It will also make a call to weight of mutex. Okay, because mutex is 0, so this process is also must wait to enter into critical section. Now what is observed? Only one process P1 entered into critical section. The other processes are waiting. Okay. Now P1 completes to execute the critical section. So once the P1 completes, what it will do? It will execute the operation called signal. It will execute the operation called signal. So signal of mutex. Tell me signal of mutex means it will increment the semaphore variable. The job of mutex signal is what? Increment the semaphore variable. Now what happens to my semaphore variable? 0 now becomes what is that? 1. 0 now it will become turned as 1. Okay. So who are continuously executing in the while loop? P2 is continuously in while loop. P3 is continuously waiting in the while loop. Now, let us suppose P3 got the chance to execute. Tell me, weight of mutex is success here because it is 1, not less than or equal to 0. So that it will do decrement. It will decrement the semaphore variable and and it will enters into what is that critical section. After that, what it will do again? It will call signal on mutex. When I say signal on mutex, okay, so 0 will become 1. So who is continuously calling the wait? P2 is now calling. Then P2 will enter and calls the wait so that it will become 0, so that it will got the chance to enter into critical section. Finally, it will also make signal of mutex. So signal of mutex. Now semaphore is available for us. So with this understanding, first thing is binary semaphore will have a value either 1 or 0. Second thing, when several processes competing to enter into critical section, only one process is allowed and all other processes will be continuously waiting in the loop. Okay, that's why binary semaphore is used for achieving mutual exclusion for a critical section problem. Okay, so this is the first kind of semaphore, binary semaphore. What is the process structure? When process wants to enter, it will first call wait on mutex. If chance comes, it will execute. After the critical section is completed, it will do the give the signal. So signal will increment the mutex variable. It has only the value either 0 or 1, initially set to 1 for mutual exclusion. The second type of semaphore is counting semaphore. Okay. So what is this counting semaphore? We will see with one example. Counting semaphore can have a value from 0 to any range. It is not like 0 or 1. You can take the value 0 to any range. Okay. So where it is particularly useful, if you take a producer consumer problem, producer has to know number of empty buffers. There I can use a counting semaphore variable. Consumer wants to know number of full buffers. There I have to use a semaphore variable, which is counting, because counting semaphore can have the value more than other than 0, 1. Sorry, not other than 0, 1. It can have a range of values from 0 to any value. Okay. Particularly, these counting semaphores are used for resources allocation among several processes. Let us take one example first. Okay, I have a resource called printer. I have a resource called printer. That printer is available in three copies. That printer is available three copies. Means what? Three printers are associated with my system. Okay, let us assume five processes wants to use this particular printer: P1, P2, P3, P4, and P5. So five processes, cooperating processes, wants to use the three printer instances. Okay. So number of instances of this printer is what? Three. Now, what is this counting semaphore? There will be one variable called semaphore variable. Let us call it as a counter. This counter is initialized to number of instances available of a printer type. So initially counter is set to what is that? 3. Okay. Next. Let us suppose P1 wants to enter into the system. P1 wants to use that particular printer. Then P1 first will make a call to wait on this particular counter. Wait on the counter. As you know, when I say wait on counter, the counter value will be decremented. Okay. So that let us name this printer as a PR1. So PR1 is now used by P1 process. Okay. Printer 1 is using by P1 process. Now let us suppose P2 wants to enter into the use the printer. Use the printer. Then what it will do? It will call wait of a counter, wait of counter, so that the counter variable will be decremented to 1, and it is ready to use printer 2. So printer 2 is used by what? P2 process. Similarly, so P3 wants to use the printer. Then what P3 will do? So P3 will call wait of this counter variable, so that counter value is set to 0. Now printer 3 will be using. Printer 3 will be using. So finally what happened? Three printers, PR1, PR2, and PR3 will be given to three processes. Still have two processes. But before that, if the counter value means semaphore value is 0, means all the resources are occupied. Because I have three instances of printers, all the three instances are occupied. If any other process wants, they must wait. How they are waiting, we will see now. Let us suppose P4 wants to use the printer. Then what it will do? It will make a call to wait of counter. Tell me, in the wait function, S is less than or equal to 0. Because S is less than or equal to 0, so P4 must wait to use the printer. Now, P5 wants to use the printer. Now, P5 will also do what? Wait of C. So, Because counter variable is a zero, this is also continuously waiting. Means once semaphore value reaches to zero, right? Any other process wish to use the resource, they must wait. Next, once wait operation is done, okay. Now, how that printer will be released? For that, let us suppose P1 completed its task. Once P1 completes the task, it will call the operation signal of that counter variable. Okay. As we know, when you give signal, the counter variable value will be incremented. When it is incremented, there are two processes who are continuously waiting to use the printer. Let us suppose P5 got the chance. When P5 get the chance, it will decrement the semaphore variable so that 1 will becomes 0. And which printer I am using? PR1 because PR1 is released already. So PR1 is used. Later, printer 2 completed the task. Then what it will do? It will give signal of counter so that the counter variable is set to 1, increments to 1. Who is waiting here? So process P4 is waiting. It will execute again wait system call. Then again 1 will becomes what? 0. This will get the chance to use the printer. Let us call it as PR2. So finally what happened? PR1 is in the hands of P5. PR2 is in the hands of P4. PR3 is still used by P3 process. Okay. So once all these three processes also completes, three times the signal is executed so the signal incrementation leads to final value again what? 3. Right? Again 3 means what? All the resources are released by the processes. So what happens with the counting semaphore? In a counting semaphore, the semaphore variable will have a value 0 or anything. It is used to give resource allocation among processes with available instances. When a process wants to use the resource, first it will call wait operation. When a process completes its resource usage, then it will perform signal operation. Whenever count value goes to 0 means all the resources are being used. If any process tries to use the resource, at that time the process must wait. This is how resources are allocated among the processes. So two types of semaphores. One is binary semaphore for mutual exclusion, counting semaphore for giving controlled access of resources to the processes. Okay. So in the next session, we will see the different uses of semaphores and what are the problems with this wait and signal operation and where we will use in applications to these semaphores.